So welcome all of you. This is the last video of this topic uh, or of this course, one and two dimension image spectroscopy for the chemist. And so first I will introduce myself. This is Vijay Rane. I'm a Prime Minister Research Fellow in the IIT Delhi. And today we will look for some problems from the assignment. So yeah, we'll directly move to the problem. But before going to the problems from the assignment. Does anyone have any problems or any question regarding the topic which are covered in the week 12? I mean, if you don't have any doubt, we'll directly move to the questions. So here, first question is based on let's select the first question states in the coupled HSQC spectrum of the compound CH3 C double bond O CH2 CH3. So if you look at the structure, it will be the in this manner, right? So the cross peak multiplicity pattern in the proton dimension for carbon A, B, and C will be. So for this one, it is singlet for carbon A. So for this one, it will be a singlet, and the triplet for the carbon B. So it will be triplet for carbon B, and it will be the quadruplet for carbon C. So this is the option answer, correct option answer here. So why this is one? So if you look at the NMR active nuclei in this compound, so it has this carbon which attached to the carbonyl carbon, right? Then again there will be another carbon, and these are the carbons present in the molecule. And if you look at the hydrogen attached uh, to this molecule, so this is the structure of this one. So the carbon one will show the singlet because there is no any adjacent carbon which has the CH2, because we are taking HSQC experiment, right? So that decoupled carbon is different than the HSQC. What happened in the carbon, sorry, coupled or decoupled, we do the spectra, carbon 13C spectra as a coupled spectra. So in that one, in the coupled spectra for, let's say in this one, for this carbon, so the carbon A, we get a quadrate, right? Because there will be a three NMR active nucleus present to adjacent to this carbon. So you get the quadrate in the proton coupled spectra. In the proton decoupled, so proton coupled, right? In the proton decoupled 13C, we get only the singlet for each and every carbon, because there will be no in the decoupled carbon spectra, we don't get any splitting due to these hydrogens. But in case of HSQC experiment, so what happened? The adjacent the carbon, we show the splitting due to the NMR active nuclei present on the adjacent carbon. So in this one, the this is the adjacent carbon, right? So if you look at, I will just take another pen. So here, yeah. So if you look at this carbon, there is no any adjacent nuclei, so that's why it shows the singlet. If you look at the second carbon, it has the adjacent carbon which has the NMR active nuclei, the three, so it will show a quadrate, right? And the third carbon, so the carbon C, which has the adjacent triplet of quadrate for the. So this carbon will show the split of quadrate. So I think they have also taken consideration the splitting due to the adjacent, the direct attached nuclei as well in this case. And the for the carbon C, it will be a triplet of, sorry, quadrate of triplet. So because there are four carbon directly attached and the two adjacent, so it will be quadrate of triplet of this one. This will be the triplet of quadrate. And for this one, So the singlet is, I don't think the singlet should be here. Yeah, I have doubt in this one. So it should not be the singlet, then it should be the quadrate because there are one, two, and three NMR active nuclei attached here. So the option A is the option here that you need to select in this question. In the second question, assuming the J3 coupling, hydrogen-hydrogen coupling, right? So if you have the carbon-carbon, so it's like one, two, three bond coupling, right? So J3 coupling or observed in a 45-degree tilted 2D J resolve spectrum of molecule CH3, CH2, C double bond O, CH2, CH3. So the multiplicity pattern in the indirect dimension will be, so for this one, it will be a two quadrates and the two triplet is the correct option in this one. In the next question, it is multiple selective questions. So in this one, the deuterium is used for the locking in all the NMR spectrometer. So if 1H NMR spectra is obtained using the protonated solvent, so what will happen? So in this case, so drifting of the external magnetic field B0 cannot be arrested. And the second is it is not possible to homogenize the magnetic field. So these are the two reasons. That's why we generally, most all time take the record the NMR spectra in the deuterated solvent. And we do the locking with respect to this deuterium peak of this particular solvent. In case of CdCl3, so it will be a 7.26 that range. The signal for this, sorry, in case of the whichever hydrogen which is not getting replaced, so that will be a CHCl3. So for this one, we know that we observe the NMR signal at 7.26. So while calibrating also, when we get the NMR spectra, we generally get the one TMS peak. But nowadays, we are not using the CDCl3 with the TMS. So because there is a small amount of this chloro hydrogen CHCl3 impurity present, so we can directly lock with respect to that peak as well. The next question is all the present day NMR spectrometer make the use of superconducting magnet, and why are the superconducting magnets are used? So the superconducting magnets are used to achieve stronger and homogeneous magnetic field. This is the first option, and the second is the superconducting magnet works in the persistent current mode. So this is the persistent current mode is important and do not require continuous supply of the electricity. So these are the two reasons we use the superconducting magnet in mass spectrometer. In the next question, the pre-induction decay signal is exponential. The Fourier transformation of the signal gives the frequency spectrum containing number of frequencies whose line shapes are, these are the Lorentzian. Uh, Generally, you see the Gaussians. These are the kind of like frequency spectra. We got sometime we got the Gaussian, sometime Lorentzian. There are multiple. This is also one of the type of the frequency spectra, tetrapodial. So, but in case of the our Fourier transform of the NMR, this it will be a Lorentzian. In the next question, the application of 180-degree pulse in the direction perpendicular to the Z magnetization result in the zero signal. So the zero signal is the correct option in this case. The next question is, in an experiment, the spectral width was 2000 hertz, sorry, 20,000 hertz. The data was acquired with 32,768 points. So what will be the achievable digital resolution? So in this case, the digital resolution in this case will be the 1.22 hertz. So So there will be a somewhere some formula to calculate how to calculate. So it is in already in the text given in the text transcript, right? So you can look that transcript for this week. So there you will get the so what is the formula, how to calculate the achievable resolution. In the question, it mentioned in the 1H NMR spectra acquired for 1 hour gives the signal to noise ratio, right? SN stands for 100. How much would be the SN if the S by N if the signal intensity acquired for 16 hour? In this case, it will be a 400, this signal to noise ratio. In the next question, if the 120, oh, sorry, 270-degree pulse is applied to applied along y-axis, the magnetation is tilted from z-axis to x-axis. So this is the option here.
Đấy. Ừ.
And in the next question, the magnetation is brought to plus x-axis and the detector is kept along. If the magnetation is brought to plus x-axis and detector is also kept along the plus x-axis, the real part of the spectrum is absorptive and the imaginary part is dispersive. So these are the some questions that I have directly taken from assignment. So if anybody on interested to knowing how to process the NMR spectra and all, so I can show you one of the example. So this is the last video uh, for this course. So hope you guys attend the examination as well. So I will show one example for the particularly I will show only 1H and the 13C spectra, how we process. So this is the 1H spectra for one of the molecule, and so I will show from starting how do we process this. So from NMR arrangement, we generally get this sort of uh, NMR data. And if you zoom this NMR data, so see in this one, there is no any TMS used in the CDCL3. So in this case, when we initially take the NMR, we generally do the calibrate the spectra with respect to the peak due to the solvent. So this is the spectra taken in the CDCL3. So if you look at here, so we can select this peak and calibrate this as a this with respect to the CHCl3. So this peak is arise due to the CH chloroform, right? Chloroform impurity. So whenever we get the spectra, we have to calibrate the spectra. So I just selected as a that spectra, and so this the baseline, not baseline, but the spectra automatically calibrate with respect to this uh, CDCl3, sorry, CHCl3 peak, and there is no any TMS peak you can see here. And this is the spectra of one of the molecule. So I will show the structure of this molecule. So the structure of this molecule is in this way. The OH, and there are multiple hydrogens present for this molecule, right? So, and as you see this molecule, it has the one OH peak. So if you look at the spectra, it has very one, if you just resolve by scrolling mouse, just take this in upward direction. So you can see there is one peak here. So that peak is due to the OH. I have just integrated that one and I will just delete all. All right. So I see there are multiple aromatic signals available, and also there is one signal in around 12 to 13 also available. So I just zoom out all this one and selected particularly aromatic region. And I see there are multiple peaks are available in the aromatic region. So initially, if you look at the structure of our molecule, it has all the seven type of signals. They are different, right? Distinguished seven aromatic protons and one OH proton. So each peak will be due to the one hydrogen in this case. So if you look at the spectra, so I just do the integration. This is open in the Mr. Noah software. So I just type I. So I did I and I selected this region. So this will be due to the one hydrogen. And with respect to this, I just selected all the peak. So if you look at the peaks, you can see here. So all peaks, these peaks are due to one hydrogen. And also, if you look at this region between 7.3 to 7.45, there are multiple peaks. They are overlap with each other. In this case, we can't do much to get the resolution because it is already overlap from on one another. I will integrate all these together. So I just integrated all. So these signals are due to the two peaks, right? So this multiple multiplet. So if you look at the total, how many total peaks are available for this molecule? So I will just also integrate this for the peak around 12 to 13. So if you just do the integration, so this is also due to one hydrogen. You can see here. So this is how the spectra you should also get when whenever you are recording the NMR spectra for the 1H NMR spectra. So I just zoom the aromatic region. So if you look at, there was one proton due to OH at around 12 to 13 ppm, and 1, 2, 3, 4. This is 5, 6, 7, and 8. So total, right? Sorry. In this molecule also there are 8 protons, right? So 1, 2, 3, 4, 5, 6, 7, 8 protons are available. So in this way, right? This is the NMR spectra is correct. I mean, if the signal is matches. If you look at the multiplicity, so multiplicity should also matches. Then I will just distinguish these protons in the two different types. So one type will be the doublet. So this will be doublet, right? These protons will be doublet. So how many doublets? There are four doublets present, and there are one, two, three, four triplets are present. So does the same matches with the our NMR spectra? So I have zoomed just the aromatic region, and if you look at the closely to this NMR spectra, so 1, 2, 3, 4, and here in between sorry, 1, 2, 3, and 4. These are the four. I will just take the spectra to these slides so I can mark there itself. So if you look at the spectra, in the spectra, there are 1, 2, 3, and 4. These are the four doublets, right? And how many triplets present? So this is one triplet. This is another second, third, and four. So four doublet and four triplets are present. So it means our NMR spectra is matches with uh, the NMR spectra for the compound. So this is how we have to check the whether our whatever the spectra we got is due to the same compound or not, or our compound which we are aiming to synthesize, do we got the same molecule or not. So you can check with the NMR spectra with the using 1H NMR. So also this OH is present. If you look at the aromatic, we have already seen there is one spectra, one signal near 12 to 13. So why this shows this broad peak? Because it is a OH peak, and we know the OH, NH, this sort of peaks generally shows a broad spectra. So OH, NH, or if there is SH, this sort of bond, this hydrogen, it shows a broad signal most of times. Not always, but most of time it shows this hydrogens, and they are exchangeable. So if you are just D2O in the NMR in the same compound, we may not get this the peak at this 12 to 13, because that will be get exchange with the this OH will get exchanged with the uh, deuterium. So that's why this peak is, uh, 12 to 13. So that's why this peak is, uh, 12 to 13. So that's why this peak is, uh, 12 to 13. So that's why the this peak is, deuterium. So that's why the this peak is, deuterium. So that's why 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 this peak is, deut will not observe in the spectra. This technique is called deuterium exchange. So if, we have to confirm whether in our molecule that OH bond or whatever bond we are looking for, like OH, NH, they are present or not. So we can simply do the deuterium exchange. So this is how we can able to open see the 1H NMR spectra. We can process this one. So in case of 13C, so I will just see whether I have any 13C spectra. So I have one molecule here. So right, so this is the 13C spectra of one of my molecule, and which has the peaks in the aromatic region as well as aliphatic region. So if you just see, someone in the past few videos back, someone asked me the question in 13C spectra, this CDCl3 or this spectra, we show the triplet. So this triplet in the carbon nanospectra is due to the CDCl3. So don't miss. In 1H spectra, we observe one peak at 7.26. This is due to the CHCl3 impurity present in the CDCl3. So don't get confused in this one. Often I have saw many people do mistake in this one. But if you look at the 13C NY spectra, we observe the peak at 76, 77, 78. That sort of range we can see here also. So you can see 76, 77 or sorry 76 to 77. So in this region, I'll just level 76, 76.5 and 77 in this one. We get a triplet, and this triplet is due to the CDCl3. Because if you look at the 2Ni plus 1 on this formula, so for deuterium, the I value is equal to the 1. So that's why we get the triplet here. Although we have only one triplet, but if you look at this formula, so 2 multiplied by n is one deuterium present, multiplied by I is 1 here and plus 1. So if you calculate this one, it will be a simply 3. So that's why we get the triplet in the CDCl3, sorry, C13 spectra, right? So don't get confused in this case. So we get the triplet in the CDCl, triplet due to the CDCl3 in the 13C, and we get the sharp singlet in the 1H spectra at 7.26, which is due to the CHCl3 impurity present in the CDCl3. That due to the impurity of the CHCl3 chloroform. So this is the sorry, the 13C spectra, and this is the uh, 1H spectra. So if you have to do the peak, we need to do the peak picking. That is, we have to where the spectra lies. So if you look at go to here, so there will be a option. We can do the peak. We can do the peak picking peak by peak, or uh, we can do the automatic or option means we can set the baseline as per our this one. So in this one you can see the all peaks are here, so I just apply as it is. So okay, so this almost all the peaks are getting peaked due automatically. But if you look at here, this peak is not getting peaked, so I just again pick manually this peak. So I can select this manually also. So I just selected this peak also, right? So we can do like this peak picking, and to look the spectra somewhat decently, I mean good. So we have to do this. We have to select the range from 0 to up to where our signals are, right? In this case, I will just select it 0 to 15. So and also, if you look at this spectra doesn't make any sense because this is completely most all the space is blank. So we can directly we can zoom this spectral region and put uh, in the blank space here. So I just let's hide this one. Not able to select this region. Right. So I can able to, yeah. So you can see, I can zoom this much region and put this region somewhere. So you can see here, I have put kept this region here. So this is how we can generally, right. So now the spectra looks somewhat good, right? So this how you also have to do when you are doing the, so I will just take this to this side because this side is completely blank, right? And you can see here and select the only region where the actual peaks are available. So this is how you can do it, and also delete the peak from this region because already here peaks are present, right? So I will select here and delete manually. So I will just delete from this for the peak for this region, and now the spectra is ready in terms of publishable quality, right? So you can see here, right? So this is how you have to you also need to uh, show the spectra. Now this spectra, I can directly control all, select all, and control C. I can directly paste in the wherever I want to paste. So I can paste directly on the slide also or else, right? And the crop the spectra and keep the spectra right. So if you look at this spectra, the quality of spectra are also good. You can if you zoom whatever amount you can see the resolution doesn't go down. So this is how you can process the 1 inch inner spectra, and similar for the 13C also. In the 13C, you don't require to do anything. You just do need to do. You can directly do the peak picking. So the by peak picking, there will be option. You can select the peak. I'll just change this number. If you just increase it 9, so you can see this line it goes up. So if you just 10, this again go up. I will just select the 15. So you can see the baseline peaks are neglected and only our the peaks due to our compound is applied here. I will just again recheck whether all the peaks are getting there or not. So you can see here all peaks are almost selected, and select the same manner, select all, control C, and I will just paste it in the another slide. So right, so this how you can also paste the 13C NMR spectra. Also try to neglect delete this the title whatever you have. So you can to delete the titles or names, you can go to the properties and common. These titles you can remove. So you can see there was initially the titles present here. You can see these titles are turned off now. So you can paste this kind of sector. Also you can do the zoom version of all this spectra also, like aromatic region only. You can make the spectra in the two pages, like on one page the only aromatic region and on one page only aliphatic region in this way. If you have time, I can show some 2D NMR spectra also. How do we generally show the 2D NMR spectra? Let me check any I have any data of the 2D. So I don't have right now the 2D NMR data. But anyway, the 2D NMR data that I think last time I have shown you the how we process this 2D spectra, right? So I think this is all for today. So does anyone have any doubt? I will just stop recording. So yeah.